Thank you, John. It's now my pleasure to introduce Smriti Chopra and Jason Mercer from ClearPath Robotics, which is a company that specializes in the design and production of robots for large-scale outdoor deployment. Smriti and Jason, you should already be having co-host privileges, so you should be able to share your screen.
Okay, awesome. All right. So can everybody see my screen?
Yeah.
Okay, perfect. Thank you, Siddharth. Hi, my name is Smriti Chopra, and I'll be co-presenting this talk with Jason Mercer. I am originally from Georgia Tech. My research focused on spatiotemporal multi-robot routing back in the day. And when I graduated about in 2015, I went ahead and joined ClearPath Robotics. Actually, their industrial division, Siddharth, so not the outdoor division, but the autonomous mobile robotic division, the industrial division, which was later then renamed Automotors. That's where I met Jason Mercer. He is the head of the controls and navigation department there. And today we thought we'll talk a little about, traffic control strategies that we employed for those industrial spaces. So AMRs in industrial spaces, basically the goal there is material handling. And in a nutshell, in its simplistic form, it is basically point-to-point deliveries. You have lots of robots and you have to get them to deliver product from different points of the facility and as required by the customer. And the biggest challenge there, honestly, is these are facilities that are not designed for our robots. So clearly, from a space perspective, oh my God, we are constantly starved for space. We are fighting with lots of other, material handling equipment like tuggers and push carts and forklifts, people walking by, boxes falling down. So it's a highly dynamic and highly constrained environment. By the very nature of our goals that we are deploying multiple robots, traffic control becomes absolutely crucial towards any sort of scalable deployment. So as long as you have 1 or 2 robots, 3, 4 robots, you can kind of be okay. But the minute you want to actually start, increasing your throughput and adding more robots, you're in a pickle if your robots are not cooperating. This is an example of our Auto 100 robots that are just running around in the test center. They have some level of congestion control enabled, and that's why we can see this high density. Usually we have no such space available in an actual facility, but we couldn't obviously show those videos. All right, so I thought we'll start with a high-level framework of what is the linchpin between all these deployments, which is a facility map. And this is really what every robot has. This is what the fleet manager sees, and this is where all our users or systems level people go in and configure with points of interest. So where do the robots, charge? Where should they park? What are like constraints, if there are any? Like for example, just basic roads, basic highways, stuff like that. Robots are going to be navigating and localizing on this map, and the fleet manager will be doing all sort of dispatch and control using this. So this is basically the most common framework here. Traffic control areas in this most simplistic sense are over 3 levels. One very obvious level is the fleet level. That's where you actually decide, the fleet manager will decide, okay, which robots go where, so assignment and routing tasks. Then of course you have the robot level where you want to do local congestion control. And when I joined the company in 2016 or 15, none of that existed. So we had absolutely no fleet level control. We used to do something like a round robin to decide which robot goes where. So there was no spatial consideration, there was no optimization. Our robots were super smart, but exceptionally greedy and had absolutely no cooperation whatsoever with other robots. So basically, whenever we would get into a pickle with respect to traffic, it would come down to our system deployment guys to go and over constrain the map with queue points and lanes and exclusion zones, and just try to sort of constrain and bit slap the robots into basically behaving, right? And that took a lot of hours and a lot of money and a lot of heartache. So that was where we started. So today, Jason and I thought that it would be fun to just kind of do a, very high level walkthrough of sort of like the conception of distributed control at ClearPath, and how it evolved, and then where it's hopefully headed now, from basically nothing to something. So here's an example problem just to set the stage. So when I joined the company, we came up with a sort of toy problem of the worst case scenario, where we have these 6 robots that are just charging at each other at full speed. And this is usually an example of what happens. So they're all greedy, they're all just reacting, they are not at all aware that the dynamic obstacle they are interacting with is indeed one from their fleet, so they could be a little smarter than just assuming it's anything that's walking in front of them. And what ends up happening is then they stop and they replan and they try to execute recoveries and end up in a spaghetti monster. This is still a simplistic example. If you can imagine that the minute you start scaling this, it can become an absolute nightmare to untangle. So with this in mind, we'll just look at different levels of solutions that we started, basically with the simplest one, and then how we moved ahead to sort of introduce this level of distributed control that we weren't at all aware of. The reason we are looking at the robot level, just to be clear, and not the fleet level, is because that was our department. We were in the navigation and controls department, which was the robot level department, and we did not have any control over higher level assignments. We just had to go where we were told to go. We couldn't really influence that part. So we did whatever best we could on the underlying part. All right. So here is our first brush with distributed control. So this is an N-way stop sign, pretty much like any traffic stop sign. It requires user configuration. It's a zone, a 2-dimensional polygon that you would draw on the map that we discussed earlier. And in its simplest form, it's a distributed FIFO queue that every robot is maintaining. So from the perspective of robot I, you have a neighborhood, just like in all distributed systems. Robot I can share data with other robots within a certain radius of I. We call that the sensor range. And the data that we are sharing is the position of our neighbor robots and their footprint. And by footprint, it's just a proxy for basically their size. And here, every robot is executing this very simple algorithm upon approaching an intersection. It's identical and it's lightweight, and it just basically sees, hey, am I interacting with this intersection zone? If I am, which means my footprint, or I am basically in some way overlapping with the zone, I'm going to look at all my neighbors. I'm going to figure out whether they are interacting with the zones. For everybody that reaches after me, I don't care. Everybody who's before me, I'm just going to simply wait for my queue to finish emptying out. And once it does, I'm going to move. Till it doesn't, I'm going to stop. So it was a very simple stop and go distributed algorithm. Our first brush. And I think this kind of laid the framework and introduced the company to the notion of distributed control. Of course, there were corner cases because this was a inference-based algorithm. So if you approach the intersection at the same time, for instance, and you ended up adding each other in your queues and started waiting for each other, simple corner cases like that, which were not very often, I would say, but had to be considered. So those were things that you could obviously account for, like you could do a random back off, or you could do what you would do otherwise in a real life scenario where you would yield to the left or something like that. One big thing about these deployments, once they go into actual facilities, is also you cannot afford manual intervention. So if a robot actually dies, for example, in the middle of an intersection, or somebody dropped a box and forgot about it, we can't have all the other robots just piling up and waiting, because that's just mayhem and you get angry calls from customers. So those kind of contingencies have to also be worked into these sort of algorithms. So keeping that in mind when you're designing is extremely important, coming from basically academia, where you don't have to think about all these other random corner cases that can happen. So, but that was fun. This was something we all enjoyed. Just going back to the example that we had earlier, now you see that every robot is waiting patiently, and thankfully, at least, we are not like tied up in knots. We can move, and this is completely distributed. Advantages, of course, was that it's very intuitive. Everybody understood it, and it was a very fast implementation. That's another constraint, right? You're deploying into a running facility, so you don't really have the luxury of taking your time implementing stuff. You need stopgap solutions. So this really helped us reach that point fast. It's incredibly lightweight, and it's minimally invasive. It's just a stop and go control, and we got instant relief in multiple deployments where we were like, oh god, this is too hairy. Limitations are that it still requires user configuration. I mean, we still have to go in and make this zone, and we still have to kind of understand certain things like, hey, do we have enough room for the robots to stop and the robots to enter and exit? And anything that requires user configuration is generally not particularly nice. It is obviously limited by sensing range. If my zone is so big that I can't see the robot on the other side, what am I going to do then, right? So it has limitations, but mostly as roboticists, it's inefficient as hell, especially if you're using it as a generic congestion control algorithm. Of course, if you're using it where you need a stop sign, sure, it's amazing, it's predictable, but we had bigger problems. We wanted to basically reduce congestion, and dropping these all over the facility was really not the answer for it. So it was a good introduction. This is what brought us to our second entry, which was coordination or distributed speed regulation. So like I said, stopping has costs. Of course, the zone is one version of it where you have to, configure it and commissioning time, blah, blah, blah. But even otherwise, it eats up space. The robots are just sitting in the middle of factories. It wears down the vehicles. You don't want to brake continuously, and it increases mission times, which is like a complete and utter no-no. So we were toying with the idea, which is that, if only we could make small changes in speed early on, preemptively, we could maybe make the robots miss each other entirely. And we should definitely make use of the fact that, these robots are not just any other dynamic obstacle. They are basically from our own fleet. So we can do something smart here, knowing that this is who we are interacting with. So the whole point here was that we don't want to stop. We don't want to replan. We don't want to reach a point where, we are wasting time. Let's just try to be a little more preemptive and cooperative. And that gave birth to our distributed speed regulation algorithm. Again, this is a very incredibly lightweight algorithm. We added one extra piece of information to our shared data, which was intent. So where does my robot or this robot intend to be in, say, 3 seconds in the future or 4 seconds in the future? So it was some very lightweight proxy of its trajectory in the future. And using just this information and a very simple geometric analysis that we can discuss maybe. I seem to be running out of time. Anyway, so the main purpose of this algorithm, again, was that every robot is going to decide a role with every other robot in its neighborhood. And the role is going to be either a leader or a follower. A leader means that I don't give two hoots. I don't care. I'm just going to do what I was going to do anyway. If I am a follower, then I apply some sort of speed regulation based on kind of interaction. So that was the whole gist of this algorithm. Here we show that basically between every pairwise robot, you can have different interaction states. Either you could be converging at any given time, or you could be maybe lagging, or you could be diverging, right? And this comes back to what I said, where you basically decide per pairwise robot whether you're going to be a leader or a follower to that robot. And then what every robot does, it calculates the set of candidate leaders and then chooses, let's say, the closest one and regulates its speed against it. So it's identical, and it's pretty resilient based on simply the intent. So, just knowing where the robots are intending to go, we were able to come up with non-conflicting good congestion control solutions. Here's an example of the control that we use to regulate the speed. If we were converging, we basically, our main aim was that we want to let the leader pass without affecting its speed or letting it know that we are, trying to hone into it. And we want to stop so that we don't end up replanning. So well in time, slow down or stop. And if we ended up lagging, then we want to just nicely slot in behind the leader and sort of follow its speed in some sense, so that you automatically maintain spacing and sort of gets, this emergent queuing, platooning behavior for free. And here's an example of basically the same star algorithm that we have, but now with this. And it's better to watch. At least it feels like, okay, now they're not silly, and they seem to be yielding with each other. They seem to be intelligent. It's great. Advantages, of course, like I said, with lightweight. Another very big advantage was that it's a very filter-like algorithm. So safety is a huge concern in industrial solutions, because these robots are moving around people and everything. So you definitely, when you're making something new, you cannot compromise or go back on a certain level of safety that you've already established. So the fact that this was a filter on top of what the robot already did and didn't really change the intrinsic behavior of the robot was very good for us. Limitations were, again, not really limitations, but we are doing speed regulation, basically. So we need our underlying problem to be feasible. If two robots do meet head on and there is nothing that they can do, then you really want a solution that will modify the paths intelligently. So some sort of cooperative path planning. This was not that. This was more of just trying to avoid congestions, but keeping your plans same. And of course, it's challenging to debug. Oh my God. And that's where one of our colleagues came up with this beautiful interface for us to be able to visualize what is happening. And that's what you see over here, much to the dismay of a lot of people, because it hogs our bandwidth. But these arrows tell you real time, basically, what is the interaction state of a robot with respect to its data. So if it's red, then it's kind of lagging behind the reader. And if it's green, then it's converging. It gives you an insight into who's interacting with who at what time and why the hell are they making the decisions that they're making. All right, real quick then, so this is coordination in real environments. So yeah, up until now we saw simulations. These are two views. On the left is a 1500 fleet, on the right is a 100 fleet. You can see that there's a lot of yielding happening. The robots seem to be behaving well in general. And we're definitely not, getting stuck for hours. Here's a time-lapse video, and usually it would end in the morning with us finding, a bunch of dead robots. But thankfully, we were able to solve a lot of problems with an exceptionally easy and lightweight solution. So I think I'm gonna just hint at another problem that we wanted to solve, which was distributed traffic control. So this was solutions where, we talked about this earlier, where you have a limited sensing range, right? So for areas where you have really long, narrow corridors or bottlenecks, or even goals inside these narrow, constricted places, communication is almost crucial to doing any sort of intelligent behavior. Otherwise, you end up being highly inefficient. So we came up with this notion of the puppeteer zone, which allows robots over really long distances to just selectively communicate with each other and be able to allow simultaneous non-conflicting movements inside. This is just an example of that idea. And basically, you're allowing robots to minimize the maximum wait time at any given point. And so the robots that turn red are the ones that are next in line to move. And so they're just basically talking with each other. They're now sharing a very simplified version of their paths and deciding who should go when, just so completely to avoid bottlenecks inside these really congested areas. So this was one step above coordination, where now we expanded to communication, not just shared sensor perceived data. Okay, at this point, I'm going to move over to Jason. Jason, do you want to take over?
If you could advance the slide. Yeah.
Yeah.
So with path coordination, we started with just speed regulation, but as Smriti said, that doesn't actually impact the path. In a lot of facilities, there's cases where you would like to have robots drive in different regions based on if they're interacting with other robots or different AMRs. Or if they're just free on their own. If we have a single corridor, like depicted on the right-hand side, if we're going at high speed, we want to be close to the middle. If we're trying to get by another robot, we want to scoot over to the side and maybe slow down. So this path warping is good if your mobile robots are nimble. It's not as good if your vehicles are like in excess of 20 tons and maybe 15 meters long. it's good to be smart, but sometimes you don't want them to get too smart, because the smarter they are, the more trouble they can get into. But let's have a look at what we can look at if we have smart robots and we want them to be nimble. So this is path warping. Again, we start with our initial path, and we're going to apply some local modifications to it using a distributed algorithm. The way we do this is we introduce a collaboration obstacle at the midpoint of the interaction. This is for head-on interactions. So we introduce a virtual collaboration obstacle at the midpoint. We can run some distance maps on the union of the collaboration obstacle, the environment, and the other robot. And then we can run some path optimizing minimization. So here we can have like a downhill simplex that pulls the path over to the right. And this here allows us to dynamically adjust our paths in a way that makes sense for head-on interactions. It works well for single robots passing. You can have this for platoons of robots passing. And it works well when both robots are biased over to the single side. Here's an example of it in action. This is still being developed. I'll just wait for this to start up. We are still tuning with the shape of this collaboration obstacle. And we're still kind of learning best practices and developing different methods. So the examples that I've shown so far is looking at a head-on interaction in a corridor. This can be extended to just general cases. So if we're coming up on other robots in a T-bone situation, or if we are interacting with like obstacles that might be people walking around or different robots, we can run the exact same types of algorithms, and we can tune the algorithm so that even if the other vehicle is not part of our fleet, we're going to be doing things that look sane, and that, like, if we're interacting with a human, maybe driving a forklift, they would be doing the same thing, like perhaps yielding to the right if that's the local convention of the traffic in the area. If we flip over to the next slide, please. I guess this here, if anyone wants to take a screenshot, this is just example papers that we found inspiring. Some of them were from previous ICRA conferences and workshops. And next slide. So I guess as a final statement for whether you're running a centralized or decentralized solutions, you have to decide what makes sense for what you're trying to solve. We're a big fan of decentralized solutions just because it scales very, very well. The communication overhead is quite low. And you can, like, we have fleets with 100 or 150 robots, and it works fine there. That would break down in a centralized type of architecture. But still, there's a good use for centralized management. So the fleet managers can decide which missions are selected and assigned to robots. Testing is quite challenging still, so you have to watch on your debugging tools. And if you have the option between a simple solution and a more complex solution, by all means, like, first thing, implement the simple one, see how it works, and then evaluate what it looks like in the field. Here's some of our future things. I think I will chop it off here in respect for the time for the next speaker. But yeah, these are what we're looking at as a company, and it's just fun to be exploring these types of ideas. Okay, I think there is a link in the conference notes for questions. And I just want to thank you on behalf of myself, Automotives, ClearPath, and Smriti for spending time with us.
Thank you so much, Smriti and Jason. That was amazing. I really like this perspective of taking smart and greedy robots and then trying to make them less greedy with the algorithms. We actually have a bunch of questions on Slido, more than we can get through in this short amount of time, but maybe I can ask one question. Is it possible to optimize the coordination performance? Example, minimize global path length or mission completion time by some methods?
Yes, and I think Smriti's actually done some work of that at the fleet level. So this is more for deciding which robot should be involved in which mission, and if if an agent has to change from one mission to the next. So yeah, for sure, we do global optimizations of fleet-wide interactions, because yeah, at the end of the day, the goal is still just maximizing the value to the customer. And we try to, hit it at all points, like up at the top, centralized, all the way down to the bottom for how we weight a stop sign, for instance.
Okay, cool. Smriti, I think you're muted.
Yeah, sorry. Yeah, definitely. And with different optimization criteria, we take into account distance, time, battery, for example, a combination of them. Yeah, we didn't talk about that because this is more about distributed control.
Got it. Amazing. Yeah, if you could head over to the workshop website, I think you can answer some questions offline if you have some time. And also, I would like to remind everyone that our speakers will also be there at the panel discussion later on, and we can get to some questions then too. So please keep asking. With this, I think I'll hand the floor over to Gennaro.